My name is Bob Fontana. My manager, Gary Ducat, and I are going to give this talk. It is an attempt to review or give a perspective of where storage media is. And just as a background, I'm in the IBM Systems Division. I work in advanced transducers on tape. And prior to that, I worked and manufactured advanced transducers for HDD. And prior to that, I worked in non-volatile memory applications at Texas Instruments. To me, storage media really translates to the petabyte shipments that are made in LTO tape, HDD, and NAND. And the reason I don't mention enterprise tape here is simply because that information is not publicly available. And the topics we'll talk about is what this storage landscape looks like, the exabytes, and a concept that's used in semiconductor industry called millions of square inches, and also areal density. And we'll do a comparison, as the program committee asked me, between what did things look like at the beginning of 2013 and what do things look like at the beginning of 2016. MSI stands for millions of square inches, how much you are actually manufacturing. And then we'll look at the 8-year trends and a summary. So let me give you a broad overview. The storage landscape is monitored by just tracking certain components, particularly areal density. That is to say, the number of bits you can store in a unit area, the revenue, the dollars per gigabyte, and the exabyte shipments or petabyte shipments. And it's kind of interesting to see what did we see from 2014 to 2015, and how does that reflect from 2012 to 2015. So in NAND, what we saw was a significant increase in basically, whoops, hang on. I guess this thing doesn't working, okay. Doesn't work, all right. So in NAND, what we saw was a significant increase in shipments, about 32%, but only 3% increase in revenue. In HDD, we saw minimal exabyte growth, but a significant revenue decrease. And in tape, we saw a modest increase in exabyte growth and a continuing drop of about 10%. And what you also see are the dollar per gigabyte drops for all of these. And we'll talk about this data more, but I just want you to have that as a snapshot. What's very interesting in here is to see for these sets of components, and these are not solid-state drives, this is just the component aspects of this. You can see that actually the exabyte shipments went up 6%, but the actual revenue went down, which means some of these technologies lost revenue. This is probably the most, I think, important slide in the talk. It may have been distorted because of the aspect ratio, but these are scale drawings of bit cells today in sort of the leading type of product. On the far left here with the NAND and the 3-layer cell, that's something that today goes into something like a 16 gigabyte chip, about 12 by 12 millimeters on the side. The HDD over there, that one actually is a cell size to scale that goes into a 10 terabyte drive. And what you see here is a tape cell, which goes into essentially a 10 terabyte tape cartridge. But these are sort of the scales today. And basically what I like to use and what Feynman at Caltech used at one time was there's always room at the bottom. And that was true 30 years ago, and we're running out of room at the bottom now. So the issue is, how do you try to scale from this point on? And I think this will be topics later, but let me just give you my perspective here, that you're running into a problem here, and as a consequence, you're going to impact areal density increases and dollar per gigabyte losses. Now, what NAND did was it came up with sort of a 3D cell design or multi-layer design, where they made the cell 20 times larger, but basically added 20 layers, and you process these things all together. So that's how they're going to move their technology. The HDD strategy is a little more difficult. They're trying to go to smaller writing by essentially writing harder, that is to say, magnetically more stable media, so that the smaller number of, if you want, spins in that bit cell can be stable. And with the tape strategy, there still is room at the bottom. And you can see why there's room at the bottom, simply because of the large bit cell. So that's really I think, the kernel of what we're going to be talking about today as to where technologies go. I want to stress here that the data here is publicly available. As a consequence, since enterprise tape is not necessarily shared publicly, it's not included in these talks. I think for the HDD data, it's very straightforward to grab the data from essentially the Seagate and Western Digital quarterly reports. I also want to emphasize that when I give $1 per gigabyte, it is basically the total revenue for that storage company divided by the total number of exabytes shipped. So clearly, a cost for an enterprise, or let's say an 8 terabyte drive, is a little bit different in dollars per gigabyte than something that you get where you have a 1 terabyte drive that goes into your laptop. So it's a blend, is what I'm trying to say. For NAND or flash, Samsung presentations typically always project growths. DRAM exchange gives you sort of the revenue by quarter. And again, the dollars per gigabyte is a blended value. So that includes the 2-layer, the 3-layer chip, the multi-layer devices, the devices built at 16 nanometers or 24 nanometers. And for LTO, the issue here is that revenue is kind of guarded relative to, and by the way, LTO in this case just refers to the LTO media itself, just the cartridges. It's exclusive of the drive. And Santa Clara Consulting Group had in the past given revenue, and we use that. More recently, in fact, within the last month, the LTO consortium actually published basically the essentially cartridge shipments for the last 10 years for all capacities. So that's where we gather a lot of that information. So when you take all of this information, you get a plot like this. And essentially, 8 years ago, my manager challenged me to say, where is the future going? I'm not sure if these slides will be publicly available or not, but I can provide people who want this slide, this particular slide here. This slide has been built up over 8 years. Typically in March, after the quarterly reports are announced, we try to assemble the information. And it doesn't work here, but what I'd like to point out is right below, there's one interesting statistic here which impacts sort of the manufacturing viability of the technology, and that's the one in the first sub-bullet. In HDD, it's the millions of units manufactured, and you can see that that has a downward trend. For NAND or flash, it's the millions of wafers that are produced each year, the millions of 12-inch wafers. And you can, and we'll talk about this later, but I just wanted to point that out, the vitality there. And for LTO media, it's the millions of cartridges built, and you can see a downward trend. That sort of is an impression, or gives you an impression of, if you want, the manufacturing vitality of what's going on. And just to give you here, for HDD, the average price was 5 cents a gigabyte last year. For NAND, this is at the component level, at literally the chip, the raw chip level, was about 40 cents. And for LTO, it was about 1.3 cents a gigabyte. And what I, again, want to clarify here, that's an average for the whole of last year. So one could gather here that probably right now we're pretty close to 35 cents a gigabyte for NAND at this, or flash at this point. So the first comparison is how much did we change from 2012 to 2013, or what changed in this dynamic? And what you can see on the right here in a distorted oval is essentially the total petabyte shipments in 2012. And there's about 429,000 petabytes shipped. And you notice that LTO accounted for 5% of it and NAND accounted for about 6% of it. If you fast forward to 2015, you see about a 50% growth in petabyte shipments. But what you also notice that in this pie now, more of it is occupied by NAND, less of it is occupied by HDD, and LTO or tape has kind of maintained its presence. The other thing you should understand that this environment, or these petabytes, span a whole range of usage, from the type of usages we're talking about here at this conference to basically people who use their cell phone. So I mean, it's a combination of an issue here. So some of that growth is not that you're taking business away from a technology, you're just creating new business. I'd like to give you a few definitions here, we'll refer to them later, but because in my business we make components and basically we are subject to sort of revenue needs or whatever, it's very important that we understand the revenue issues here. So first of all of our technologies rely on a manufacturing base. You have to build things. You either build 300 millimeter, you either process 300 millimeter wafers, or you build drives for HDD, or you build LTO cartridge shipments. And how do you increase exabyte shipments of storage media? Well, you either increase that by building more factory capacity or by increasing the efficiency of storing more bits per unit surface area. The latter is called areal density. So the factory capacity is millions of square inches, and the bits per unit area is areal density, commonly referred to as gigabytes or gigabits per square inch. And then you can do the simple math. The exabytes is just simply the manufacturing base times the areal density, and the revenue is the exabytes times the dollars per gigabyte. And the problem you face here is that if an industry faces downward price pressure, the amount of exabytes they ship better move up if you want to gain or maintain, if you want a revenue, not necessarily profit, but a revenue increase. Or the revenue is just your manufacturing base times the areal density times the dollars per gigabyte. So you can basically, you can toggle this any way you want to. I think you should recognize that exabyte shipments come with cost. Either factories for an increase in the manufacturing base or R&D expenditures for an areal density improvement. In general, one likes to favor the R&D expenses. They tend to be less than the capital displacement. But the comment I would like to say is that the areal density and the dollar per gigabyte metrics have really underperformed in the last 3 years relative to some measure of, if you want, a Moore's Law perspective. And really what I'm trying to convey to you here that the Moore's Law perspective of density doubling every 2 years and basically price dropping by a factor of 2 every 2 years isn't happening anymore, and probably people already recognize that. So, first of all, what did I do? This was a slide below that I showed basically on the Queen Mary 3 years ago. And I made these sort of projections. And here is kind of what happened right now if I put these things here. So there's some underperforming and overperforming. Let's concentrate NAND first. NAND was projected at 20% a year based simply and totally on lithography improving. And the reality that happened was there was a strong application or embracing of what we would call 2-bit and 3-bit per cell have actually been incorporated, coupled with the fact that the industry convinced users to accommodate lower endurance or read-write cycling. More critically, you'll notice that there's been a flip here in that the areal density in green for the NAND product is now greater than the areal density for the HDD product. And when I'm talking about areal density, I mean the local areal density. Obviously, there's a lot of overhead in a disk and in an NAND to basically have saw lines, kerf, leads, extra buffer lines, etc. So that's happened there. What happened in HDD? Well, basically what happened in HDD was HAMR was sort of that next projection, and it is a tough technology and it is moving on. And as opposed to that, HDD moved in what I would call to some incremental approaches, which might be something like shingling, it might be other issues. And to accommodate this lower areal density, HDD moved to giving you more media per unit volume with more stacks. And with tape, what happened here, we underimproved, but I think my initial projections were a little optimistic. And what really, if you look carefully at here, you can see two sets of data.